our last class we have been discussing on deadlock avoidance strategies, and in that we have seen cycle detection algorithm for single instance resources, and for multiple instances. So, there is another algorithm known as Banker's algorithm. So, we started discussing on this. So, we will continue on this in today's class. So, in the Banker's algorithm, it is applicable if there are multiple instances of resource types. So, each resource type may have multiple instances, and so the requirement is that each process must a priori claim maximum use. So, each process must declare like how many resources it wants at most for each type, and when a process requests a resource, it may have to wait, like even if the resource is available, so it may not be allocated. So, the system will try to decide like if I do this allocation, whether there is any possibility of going to a deadlock situation or not. If there is a possibility of going to a deadlock situation, then the resource will not be allocated even if the resource is available. So, when a process another condition that is there is when a process gets all its resources, it must return them in a finite amount of time. So, it is not that a process has been given all the resources and still it is just going on doing something without releasing the resource. So, within a finite amount of time all the resources given to it must be returned. So, it is based on the banking philosophy. So, think of an interest free bank where a customer establishes a line of credit in which the customer declares that what is the maximum amount of credit that he or she may need, and it borrows money in chunks that together never exceed the total line of credit. So, every time the customer needs some money, so the customer asks for some money, but at no point of time, so total money required is more than whatever is the maximum of the credit. So, once it reaches maximum, customer must pay back in a finite amount of time. So, once the total credit total borrowed money becomes equal to the credit limit, then the customer must return all the money. So, that is banking philosophy. So, it ensures that the bank itself does not get bankrupt if all the customers they ask for money within their credit limit, and then it is unable to satisfy any of the customers. So, that should not happen. So, it should be able to satisfy at least one customer, so that customer finishes off the job and returns all the money to the bank. With that money, the bank will satisfy some other customers, and then the whole system will proceed. So, that is why this algorithm is known as Banker's algorithm. So, here the system is considered to be in two different three possible states: deadlock state, and possibility of deadlock, and there is no deadlock. So, that is no possibility of deadlock, and we have seen that when there is no possibility of any deadlock to occur, so that is called a safe state. When there is a possibility of deadlock from a particular state, so that is called unsafe state, though unsafe state means it is not yet deadlocked. So, it may so happen from the unsafe state the system comes back to the safe state, but there exists a chance that the processes may request resources in such a fashion that the system may lead to a deadlock situation. So, Banker's algorithm, it works for say n number of processes and m number of resource types. So, available array, so it is a vector of length m. So, available j is equal to k if there are k instances of resource type r j available. So, it tells at any point of time how many resources of each type available. Then there is a max array, so which is n cross m matrix. Max I j, this is equal to k, means that process I may request at most k instances of resource type r j. So, you can understand the max array is a static array, because this is declared by the processes at the very beginning how many resources of how many instances of each resource type the process may need at most. So, that is the max array, and available. So, this is dynamic. So, at any point of time as the resources are being allocated to processes, so this available entries will decrease, and when the resources are returned, the available entries will again increase. Then allocation. So, this is also a dynamic array. So, it tells that it is n cross m array, the entries will change over time. So, allocation I j equal to k means process P I is allocated k instances of resource r j at this point of time. So, the need array is basically a derived matrix. So, need I j equal to k, then P I may need at most k more instances of Rj to complete the task. So, need Ij equal to max Ij minus allocation Ij. So, max is the maximum requirement of process I for resource type j, and allocation is currently allocated number of resources of type j to process I. So, their difference gives us the need, that is the maximum number of more resources that the process I may need of type j. So, the safety algorithm, so this is the major part of this Banker's algorithm. So, it works with two temporary arrays, work and finish. Work is a vector of, they are of vector length m and n respectively. So, initially work is equal to available. So, whatever is the current availability of each resource, so that is there in work, and finish I. So, finish I equal to true means the ith process has been satisfied with all its resources. So, we can consider that the process is over, process is true, it is finished. So, initially since none of the processes have been determined to be able to complete with the available resources. So, we have this finish I equal to false for all I. So, the next step is to find an I such that both finish I equal to false and need I less or equal work. So, work is currently holding the currently available number of resources that is there in the system. So, if the need of the ith process is less than the currently available resources of each type. Okay. So, then in that case we can say that whatever resources are requested by process I can be given to it. So, process I will finish off. So, finish I, so we try to determine an I such that finish I is false and need I is less or equal work. If no such I exists, then there are two possibilities, either of the two conditions A or B may become false. Okay. So, if no such I exists, then we come to step number 4. So, in this case one possibility the finish I is true for all I. So, we could not find any I for which finish I is false. So, all processes could be satisfied with their resource requirements. So, all of them are considered to be completed. So, finish I equal to true if it is all if it is true, if it is the case, in that case the system is in a safe state. So, with the currently available resources, all the maximum requests of all the processes can be satisfied. So, naturally, so that is so we can say that the system is in safe state. However, the second part, so if it is if we have come to step number 4 following the condition 2b becoming false, that means the need I is for none of the processes their need is less than whatever is currently available. So, all the processes they need more resources than that are available at present to finish off. Okay. So, maybe they will ask for all those resources and the system will not be able to allocate those resources to all the processes, none of them will finish off. So, in that case the system is in unsafe state. So, if we find that the system, so if we on the other hand if we can find such an I as it is given here. So, if we can find such an I, then we come to step number 3 and then this work array is updated as work equal to work plus allocation I, because whatever is currently allocated to process I. So, they once it is satisfied, once its requirements are satisfied, then it will return all the resources. So, work array will have all the currently allocated resources given back and finish I will become true. So, we can consider that the ith process is done and go to step number 2 again to see whether we can satisfy other processes with the currently available resources. So, in this way if we can satisfy all the processes, that means the system is deadlock free. So, this is the basic idea that we have in this safety algorithm. Now, this safety algorithm we can have an example to just before we proceed further. Suppose we have got 5 processes P0 to P4 and this there are 3 types of resources. A has got 10 instances, B has got 5 instances and C has got 7 instances. So, this is the maximum thing, the maximum resource that we have. So, basically if we go back to the algorithm, then here this one this so that is the currently available resources. So, initially the available array will have all these. Now, suppose at some point of time t naught, so this is the situation, the allocation array. So, for process P 0, it has been allocated no instance of a resource A, one instance of resource B and no instance of resource C. Similarly, process P 1, it has been allocated two instances of process of resource A, and 0 and 0 of B and C. So, like that P 2 is having 3 of A and 2 of C, like that, and this is the maximum requirement. So, this has been declared by the individual processes. So, process 0 has declared that it will require at most 7 A, 5 B and 3 C. P 1 will require at most 3 A, 2 B, 2 C. P 2 will require at most 9 A, 0 B, 2 C. So, like that. So, available at present. So, so there are 10 instances of A, out of that you see 2 plus 3 plus 2. So, 7 instances are already in use. So, 3 instances are available. Similarly, for B, 5 instances are maximum. So, we have got 1 plus 1 2 already in use. So, 3 are left, and C has got 7 instances, out of that 5 are already in use. So, 2 are available. So, this is the current availability. Now, at this situation we have to judge whether the system is safe or not. So, system will be safe if by using this 332 of ABC we can satisfy any of these processes to completion, and then that with that if that process will release the resources, with that we will proceed with the other processes. So, let us see how it goes. So, first we determine the need array. So, which is max minus allocation. So, max minus allocation if we do, so this is 753 minus 010. So, it is 743. So, that is 743. For P 2 it is 322 minus 200. So, it is 122. So, P 2 is 122. So, this is the requirement. So, P 0 can ask for at most at most 7 more instances of A, 4 more instances of B and 3 more instances of C before releasing the already held resource or one resource of type B. Similarly, P 2 without releasing the resource to 2 instances of A, it can ask for 1 2 2 of A B C, like that. So, with that, so this is the current availability. So, can we satisfy with this 332, can we satisfy any of these needs? Okay. So, you see this P 1 requires 1 2 2. So, with that with this 332 availability, so this one can be satisfied. So, we can say that this we can satisfy this one. So, P 1 is done. So, once P 1 is done, so this whatever is currently allocated to P 1, so that will also be available. So, this 332 it will become, these 2 instances will be available. So, it will become 532. Okay. These 2 instances will be available. With this 532 we can satisfy this P 3. So, so after P 1 is over, so we can give resources to P 3, so that P 3 will complete, and this 211 will be returned by that. So, 211 is returned. So, this availability will become 743. With this 743 being available, so we can satisfy this P 4. P 4 is satisfied after this. So, with that this 002 will be available. So, this will become 745, available array will become 7. Actually, this available is copied into work, if you remember. So, that work array will get updated to 745. So, this is also done. Now, after that with this 745 we can satisfy this P 2. So, 600. So, this one can be satisfied. So, P 2 can be satisfied, and this P 2, this after P 2 is over. So, these resources will be available. So, we can say it is 10 4 7 that will be available, and with this 10 4 7 we can satisfy P 1, this 743. So, P 1 can be satisfied. So, P 1 is satisfied at the end. So, at this point you see that all the sorry P 0 can be satisfied. So, this is P 0. So, in this way if you see this, all these processes could be satisfied. So, for all the processes, that finish array entry will become equal to true. So, this array will this algorithm will terminate, declaring that this current system is in, this is a safe situation. So, current situation is a safe situation. Similarly, so if you cannot find any sequence of processes by which all the process maximum requirements could be satisfied, then we will say that the system is in unsafe state. So, we will proceed with this and let us see how this algorithm can be formulated. So, the resource request algorithm for process Pi. So, we do it like this. So, let request I be the request vector for process I. So, every process makes a request, a Pi process makes a request and request I j equal to k if Pi has asked for k instances of resource type R j. So, if request I is less or equal need I, then only we go to step 2, because if resource I request I is greater than need I, that means there is an error, this is an error condition, because the process has asked for more that it initially declared. So, that is that should not be the case. So, request I less or equal need I. So, this is the condition to be satisfied, otherwise raise an error condition, the process has exceeded its maximum claim. If request I is less than available, then we have if request is more than available, then naturally the resources are not available. So, process anyway has to wait. So, if request I is greater than available, then the process has to wait, because resources are not available. If resources request is less than available, less or equal available, then we come to step number 3. We assume or pretend that we have allocated the resources to Pi by modifying the state like this. From the available, we remove the resources asked by the request I. So, available array is updated, allocation array is updated by allocation, with allocation I we update with this request I, as if all the requested resources have been allocated to Pi. So, allocation I gets updated, and need I is naturally that is decremented by request I, because need I is available minus allocation. So, that is maximum minus allocation. So, that way this need I is updated by need I minus request I. Now, after that we run the safety algorithm that we have discussed previously, and after running the algorithm, if we find that it is safe to allocate this, the system is in safe state, that means it is safe to allocate the resources requested by process Pi. So, in that case the resources requested will be allocated. Otherwise, the process, if the algorithm declares that the system will go to an unsafe state, then the process Pi must wait. So, you see here, even if the resources are available, only because there is a possibility of leading to a deadlock situation. So, this resources will not be allocated. So, the old resource allocation state will be restored. So, whatever updation we made, this temporary updation that we did for this resource available and these arrays, so they will be undone, this resource allocation step. So, available will be available plus request I, allocation I will be allocation I minus request I, and need I will be need I plus request I. So, those updations will be done, it is not written here explicitly. So, then we will try with the next request from any other process. So, this way this algorithm continues and it gets this resource allocation done. So, to have a look at this Banker's algorithm, so again we come back to an example that we did previously. So, suppose there are 5 processes P0 to P4 and there are 3 resource types, A of 10 instances, B of 5 instances and C of 7 instances. Snapshot at time T0 is like this, and we have previously analyzed that this state is a safe state. So, system is in safe state. So, there is no possibility of going to a deadlock from this particular state. Now, suppose process P1 makes a request for 102. So, first of all, the availability is availability was 332. So, the first thing we check whether request I is less than need I. So, request I less than need I, process P1 is asking for a maximum is 322. So, that check is done. So, it is okay. Then request is less than available, the 102 is less than 332. So, that is also correct. So, now we will be trying out that safety algorithm, and for that we will be looking into state of the system after resources allocated to P1. So, we will pretend that this allocation has been done to P1 and then we try to analyze the system. So, it is 0 1 0. So, this P 1 was P 1 was has requested 1 0 2. So, as a result this allocation is done. So, P 1 was having previously 2 0 0, with that 1 0 2 it becomes 3 0 2, and this need becomes, it is 3 2 2 minus 3 0 2. So, it is 0 2 0. So, this is the need, and currently available ABC available was 3 3 2. From there this 1 0 2 is subtracted. So, it becomes 2 3 0. Now, with this we have to see whether the system is in safe state or not. So, if we try to run safety algorithm on this, then we will with this 2 3 0 you can see that first this P 1 can be satisfied, because P 1 if I give it 0 2 0 resources, the 2 instances of B, then P 1 will finish off, and as a result this available array will become, this 3 0 2 will be returned. So, it will become 5 3 2. So, it will become 5 3 2. So, with this 5 3 2 P 3 can be satisfied. If P 3 is satisfied, then this 2 1 1 will be returned. So, this will become 7, then 4, then 3. Okay. So, with that this P 4 can be satisfied, this 4 3 1. So, this becomes 11, sorry, this becomes 7 4 5. So, after P 4 we can satisfy P 0, and this 0 1 0 will now be available. So, this becomes 7 5 5. So, with that we can satisfy P 2, and this 3 0 2 can be satisfied. So, that it becomes 10 5 7. So, you see that this one can be satisfied. So, this request can be satisfied. So, this is in a safe state. So, at this point of time, so we can see that this particular request by P 1. So, if this request is granted, then the system will be in safe state. So, we can satisfy, we can allocate the resources to the process P 1. So, this particular request can be satisfied, and this is a safe allocation. So, this resource will be allocated. Now, given this state, so given this, suppose we have allocated 1 0 2 to process P 1, and now process P 4 has requested for 3 3 0. So, if P 4 has requested for 3 3 0, so so this one if I try to see whether this P 4 can be granted or not. So, this 3 3 0 if it is there, then so it is becomes, the allocation becomes 3 3 2, okay. And this 3 3 0, of course, this 3 3 0 cannot be allocated, because you see this available is 2 3 0. So, it will straightway stop at that point, because 3 3 0 is not available. So, that way this cannot be done, this cannot be granted. Now, however, this 0 2 0, suppose P 0 request for 0 2 0. So, this is not possible, because not available, resource is not available. Okay. Now, what about this one, say 0 2 0. So, 0 2 0, if we give P 0, so this becomes, allocation becomes 0 3 0. Okay. So, this maximum requirement will become 7 2 3, and then this 2 3 0. So, this will change to 2 1 0. Now, with this 2 1 0 requirement, so can we satisfy any of the processes, like P 0 requires 7 2 3. So, it cannot be satisfied. P 1 requires 0 2 0. So, it cannot be satisfied. P 2 requires 6 0 0, cannot be satisfied. P 3 requires 0 1 1. So, cannot be satisfied, and then this P 4 requires 4 3 1. So, none of the processes can be completed. So, none of them will be returning, there is a possibility that none of these processes will return resources before releasing all other resources. So, this is so this one, so this particular point, so the resources are available, but the allocation is not safe, available but not safe. So, this is not safe. So, this is a situation that Banker's algorithm, it will stop the allocation. So, this allocation will also be stopped, though the resources are available. Okay. So, this way this Banker's algorithm, it does a check that whether there is any possibility of going to a deadlock situation, and if there is a possibility, then the resources will not be allocated. Okay. So, next we will be looking into the deadlock detection and recovery techniques. So, there are this will allow the system to enter into deadlock state, and then some detection algorithm will run, and the detection algorithm will determine whether there is any deadlock or not, and if there is a deadlock, it will try to recover from the deadlock situation. So, because this is important, because in many cases what happens is that there is the possibility of occurrence of deadlock is very less. So, as a result, when the system throughput becomes pretty low, even if the degree of multiprogramming is high, so we can there is a possibility of deadlock in the system. So, then this deadlock detection algorithm can run. So, it may try to see whether there is really a deadlock in the system or not, and if there is a deadlock, then it will try to recover from the deadlock. So, recovery means some of the processes that is deadlocked. So, it will be taken off from the system. So, it will be restarted also, and all the resources that are held by that process, so that will be claimed back. So, this is the way we will do the recovery. So, we will come to this recovery scheme and all. So, first one, for single instance of each resource type. So, for single instance resource type, so this is similar to the graph based algorithm that we have seen for this avoidance of deadlock. So, here we may remember we construct something called a wait for graph. So, suppose this is the resource allocation graph that we have. So, in this resource allocation graph, so you see that process P1, it is holding the resource R2 and requesting for R1. P2 is holding R1 requesting from R5, P2 is also holding R3, P2 is also asking for R3, and it is R3 is currently held by P5. Similarly, P2 is also asking for R4. So, P2 is asking for R3, R4 and R5 while it is holding R1. P3, it is holding R4 and asking for R5. P5 is not asking for anything, but it is holding R3, and P4 is holding R5 and asking for R2. So, this is the situation that we have. So, this is the resource allocation graph. Now, from this resource allocation graph, we construct another graph which is called wait for graph. Okay. So, wait for graph. So, this does not have resources, it just have processes in it. So, which process is waiting for which process? Like you see that P2 is waiting for the resource R1. P1 is waiting for the resource R1, which is currently held by P2. So, in some sense we can say that R1 will be released by P2 only after it has finished using. So, P1 is actually waiting for P2 to release R1. So, we can say P1 is waiting for P2. Similarly, P2 is waiting for the resource R4, and R4 is currently held by P3. So, P2 is actually waiting for P3. Similarly, P2 is also waiting for P5, because resources R3 is with P5. So, P2 is waiting for P5, and P2 is waiting for P4 because the resource R5 is currently held by P4. So, it is waiting for P4, and P4 is waiting for P1 because this resource 2 is held by P1, and then once P1 releases it, then only P4 can get it. So, P4 is waiting for P1. So, this way we can construct a wait for graph, and so this in this wait for graph we do not have any resource node, only the processes are the nodes, and there is an edge from process Pi to process Pj if Pi is waiting for the process Pj. So, this way we construct the wait for graph. So, this strategy is very simple. So, you start from a process, and if you find an edge going out of that process node, and whichever resource it reaches, from the resource you again take the edge going out, and then ultimately reach a process which is holding it. So, that way if you start with P1 and search by this path, so you will reach the process P2. So, accordingly we can add this edge. So, this way we can formulate this wait for graph by looking at each processes, and then going through the edges that are going out of the process node. So, this way this resource allocation this wait for graph is constructed, and once this wait for graph is constructed, so we can run a cycle detection algorithm. So, we maintain a wait for graph and periodically invoke an algorithm that searches for a cycle in the graph. If there is a cycle, then there exists a deadlock. So, basically this wait for graph is always maintained in the system, and whenever the system throughput is low, then the OS may decide that there is a possibility of deadlock. So, let me run the deadlock detection algorithm once. So, this is a cycle detection algorithm, and cycle detection, you know that it uses this some sort of depth first search algorithm, and using that algorithm, so it can try to detect a cycle in the graph. And once this, if a cycle is detected, then there is a deadlock. So, algorithm detect a cycle in a graph requires an order of n square operation, where n is the number of vertices in the graph. So, that way it is a costly operation. So, you can understand that if there are a large number of processes in the system, then this detection deadlock detection will take time. So, it is a costly operation. So, until and unless it is very much necessary, so we should not go for this deadlock detection type of algorithm. But some systems use it, because we have to, we do not use this avoidance or prevention mechanisms, and we use this detection technique. So, we will continue with this in the next class, when we discuss on the multi instance situation.